Hi guys, so this little video is going to be chapter 3, continued a little bit more details of some items, and then I feel should be covered a little bit more for our understanding of atoms. So the first thing is abbreviations that I believe are essential for us to know. So most of us know that matter is composed of solids, liquids, and gases. And solids, when we see them in a chemical equation, you're going to see them like this. Okay. Liquids, you'll see them like that. And gases, like this. Now, another symbol that you're going to see belongs to aqueous, and that's going to be AQ. Okay, so an A and a Q. And aqueous means dissolved in water. Okay, so that's what aqueous means. Now, we have a couple things that are, or chemical compounds that are diatomic. And we covered this in the last video, but I'm going to repeat it because I'm going to use that today in this one. So diatomic elements. This diatomic means they come in pairs or in twos. So come in pairs to a natural state. So only when they're in their natural state. There's only 7 of these elements, and that's going to be hydrogen, nitrogen, oxygen, chlorine, iodine, bromine, and fluorine. So whenever you see those elements by themselves, they're always going to be diatomic. That means they're always going to come in twos. All right, so we're going to talk quickly about law of conservation. Different marker, that one's running out. Law of conservation of matter. And this law basically states that matter cannot be created nor destroyed. Okay, so we cannot create nor destroy matter. Just make sure you guys can see that right now. So we're going to apply this in a little equation, something as simple as the creation of water. Okay, so in this example, I'm going to say water is formed by combining hydrogen and oxygen gases together. Okay, so we want to show this in a chemical equation. A balanced chemical equation. Okay, so we're going to show it in a balanced chemical equation, the formation of water. Okay. All right, so first things first, it says hydrogen and oxygen combined together. So I'm going to have hydrogen plus oxygen, and this combines together to form water, H2O. Now let's use some of the items we just learned. We know that hydrogen is diatomic, so it comes in twos. We also know that it's a gas, so I'm going to put parentheses G for gas. So now I'm showing that it's diatomic, and I'm giving the abbreviation in which state of matter it is in. Oxygen is the same. also diatomic, and it's in gaseous state. Water, it's liquid. Why? Water is liquid. So I'm going to put an L right there. Okay. And this molecule right here, this is a fixed quantity. This is a fixed quantity. We're not going to change that. All right. So now we've written our abbreviations down for water. And we've taken care of our diatomic elements. So there's a couple other things we need to do. We need to now meet the law of conservation of mass, make sure everything is the same on each side. So here I have 2 hydrogens. Here I have 2 oxygens. Here I have 2 hydrogens, and I have 1 oxygen. Right away I could tell that they do not match. So I need to make them match. Now, the way we do that is we multiply our items by something called the molar coefficient. So the number that's going to go there is known as the molar coefficient. All right, it's going to be known as the molar coefficient. So the numbers that go there are numbers with the common common product of each, right? I believe that's what it is. If not, it's something you're going to multiply this by in order for all the numbers to match. Watch me do it and you'll understand. Okay, 2 here, 2 here. I don't need to do anything to hydrogens so far. 2 here, only 1 there. That's not going to work. So what can I multiply 1 by to get a 2? 2. Okay. So I'm going to multiply this by 2. Now you notice that the 2 goes in front of water. So you're going to pretend like there's parentheses there. And this 2 is going to distribute to both the hydrogen and the oxygen. So now I have 2 times 2, which is going to be 4 hydrogens, 2 times 1, which is going to be 2 oxygens. Okay. 2 oxygens, 2 oxygens. My oxygens match. Okay. I have 4 hydrogens here and 2 hydrogens here. My hydrogens don't match, so now I need to multiply this 2 by something to get 4. Well, 2 times 2 gives me 4, so now I have 4 hydrogens. Hydrogens match both sides. We're good, so I'm just going to put a 1 there. And this equation is now balanced with equal amount of atoms on both sides. So it is balanced with equal number of atoms on each side. Now, just a couple of things in case you guys don't know the names of sides here. This part of my equation that's on the left side of my yield is known as the reactants. They're the things that react. And this side here, everything on the other side, is known as the product. Okay, that's going to be the product. This arrow signifies yields. So it's similar to equals, produces. Okay. All right. So now let's go into another part of the law of conservation of matter. See if I can erase this. There we go. One right at the bottom here. Now that we balance the number of atoms, we also want to balance the mass, okay, the mass of this. So in this example, let's say we used 4 grams of hydrogen and we used 32 grams of oxygen. Well, how much water are we going to produce? Well, the left must equal the right, so 32 plus 4, we produce 36 grams of water. Okay, this side must equal that side. And this is law of conservation of matter applied to a balanced chemical equation and balanced amount of mass. Okay, you cannot create and you cannot destroy matter. You can rearrange it. And this is for normal chemical reactions. And nuclear chemistry is a total different topic when it comes to this, right? That's nuclear, so we can technically destroy an atom in nuclear chemistry. All right, so now let's go into our atom itself. What does an atom look like, and what are the components and parts of an atom for us to explore? Okay. So, the atomic structure. Okay. I'm going to call this the atomic structure of an atom. Most of us already know everything about an atom. In this example, I am going to use, see this periodic table here, sodium. Okay, we're going to use sodium. So, or actually, can I use a small? Nah, sodium. All right, sodium looks like this on the periodic table. And this is actually a decimal, it's like 22.9. Okay, and we'll get into average atomic masses in a little bit. This is the atomic number. This one is the atomic mass number. And this here is the symbol. Okay. Now, the atomic number is made up of protons. The atomic mass is protons plus neutrons added together. And we're like, what are these parts? Well, an atom is composed of 3 subatomic particles. So our atom is composed of the proton, the neutron, and the electron. Okay, so an atom is composed of all of those. All right, so protons, the symbol for a proton is P with a positive, and protons are positive. Okay, they have a positive charge. They are located in the nucleus, and they have a mass of 1 AMU. AMU stands for atomic mass unit. Now this is a rounded up number for the atomic mass unit because the mass unit is actually a little bit different, but we round them up for our sake in intro chemistry and at times in Gen Chem. However, you may find the actual mass of all of these particles once you get to Gen Chem and OChem. All right, a neutron is neutral, like the name suggests. So its charge is neutral. It's also located in the nucleus, and it has a mass of 1 AMU. And one more time, in reality, that's not like the actual number. It's really, really close to it. But a neutron is actually slightly bigger than a proton. An electron is an E with a negative symbol. It is negatively charged. It is located in the electron cloud or orbit. And sometimes they call them shells, and we say that they have a mass of 0, or it's negligible. Negligible. Okay, so we actually don't know what the mass is for it. Okay. We're going to use this information to create a Bohr model. Niels Bohr was a physicist, and he actually created the Bohr model that perfectly represented the amount of energy in the first energy level for hydrogen and helium. However, his model doesn't quite work anymore for higher energy levels. And we do have a newer model. But the Bohr model is the one we use in order to demonstrate what an atom looks like and better understand it, as it is a more stable 2D kind of structure. Okay, so Bohr model. And we're using sodium. Okay, so sodium, remember, it looks like this. Okay, the number of protons is equal to 11. Because it's neutral, it has no charge. Electrons must also equal 11, right? Because this is positive, negative, add them together, it creates a neutral charge. The number of neutrons is going to be 23 minus 11. In this case, we're going to get 12. Now we're going to build our, excuse me, had to sneeze. Now we're going to build our atom. All right, in the center is our nucleus. Now I'm going to make this nice and big just to fit all of my protons and neutrons. Okay. This is going to represent my nucleus. And in my nucleus, I said I have protons and neutrons. And according to this, I have 11 protons and 12 neutrons. And just to coordinate these, I'm going to make my protons pink. And I'm going to make my neutrons yellow. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are my 11 protons. Now 12 neutrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? This here is my nucleus. And surrounding my nucleus is going to be my orbits. So my orbits, we're going to start with energy level 1. And the first energy level is very, very close to the nucleus. Not super close, but it is close. Now, this is energy level number 1. Okay? And in it are going to be my electrons. And to represent my electrons, I'm going to use this brownish color here. Okay? And I have 11 electrons. Energy level 1, however, can only hold a maximum of 2 electrons. Max of 2 electrons. So that means, so actually let me do this to help you guys out. Out of 11 electrons, I have used up 2 electrons. I have 9 electrons left to go. So I'm going to put another energy level. And I'm going to start to fill it. Now electrons, when you first put them and as you write them, make sure you follow this order. One on the top, side, bottom, side. 1, 2, 3, 4. Okay, that specific order is going to help you when it comes to creating your molecules and when we start combining things together, showing molecular combinations. Okay, following the structure will develop shapes more appropriately. So make sure you follow the 1, 2, 3, 4, north, south, west, east, whichever way you want, but you have to separate them. And after you separate them in this nice T-like fashion, then you can start grouping them up together. So I've used 4. Now I'm going to group them up. 5, 6, 7, 8. You notice that there's no more electrons to group anything up with. So I got 1 electron left to go. I'm going to create another energy level, third energy level, and I have 1 electron, and I'm going to place that 1 electron right there. All right, so a couple of things for us to know is that in energy level 1 fixed mass of 2 electrons. Energy level 2 fixed mass of 8 electrons. I feel like you guys can't see that well, so I'm gonna, here we go, fixed mass of 2 electrons. Okay. And energy level 3, right here. Well, this one kind of varies. So it fits 8 electrons, and its extended form, it could actually fit 18. Okay, so this one is in the non-extended form, and this one is in the extended form. And that's when we start talking about which orbital it's in. Is it in the s orbital, p orbital, d orbitals, chapter 4 kind of stuff. Okay. Now remember, in here, this was my nucleus. And I just realized I wrote nucleus with an E here. Ignore that E right there. There's no E there. Typo. All right. So that right there is my atomic structure. Excuse all the noise in the background. That one is my atomic structure of sodium using the Bohr model. Protons in the center, and neutrons also in the center, with electrons in the outer. Electrons pair up. Now the way that you pair up electrons when you're working on this one is going to be 1, 2, 3, 4, 5, 6, 7, 8. So you want to create a T-like shape when grouping your electrons together. Do not separate them. A common mistake that I see is you guys Google the image of what is the Bohr model of us. And it shows you with all the electrons separated, like spread out. That is incorrect. Do not do that for your atoms. Electrons pair and group up together. Do it as I'm showing you here in all of your work. Okay? Unless stated otherwise, but it shouldn't be stated otherwise. Right. Okay, now that we have here and we understand that protons are positive, electrons are negative, they cancel each other out, those charges, when they are equal. Sometimes they're not equal. Okay. So the way we create electricity is by having something called ions. Ions produce charges. Okay, so ions or ionic structures, things like that, produce charges. Okay, so electrical charges. Okay, so ions produce electrical charges. Okay, so this is like your batteries, right? You have the south and you have the north pole, those kind of things. Okay, so using sodium as our example, if I write sodium down and I write it just like this, Na, and nothing else, then this is considered neutral. But if I write sodium like this, it is no longer neutral. It is charged. It has a charge to it. Okay. I could also write sodium like, actually, I don't want to do something that's like not technically correct. So I'm just going to write those two here. Okay. So let's talk about their particles. In this neutral sodium, protons equals 11, electrons equals 11. Charges cancel each out, and it is neutral. In this sodium, Protons is equal to 11. Notice we did not change the number of protons. Electrons, I don't know. However, I do know that I end up with a positive 1 charge. Well, just do the math. 11 plus what gives me a positive 1? Well, I would say 11 plus negative 10 gives me a positive 1. And that's how we end up with that charge, is we have 1 less electron. So we have positives there. Let's show an example with something that's negative. By the way, something that is positively charged is called a cation. Cation, right? Positively charged. So it's positively charged. Now, we're going to have compounds that can be negatively charged. So let's use oxygen as our example. I could have oxygen like that, or you could see oxygen like this. Oxygen, the number of protons is 8. 8 protons. So therefore, if it's neutral, it's going to have 8 electrons. These are going to combine together to get a total charge of 0. Right here, this oxygen is negative. It has a negative 2 charge. So protons doesn't change. And I'll tell you why not. If you change the number of protons, you change the element itself. Okay, so you change the number of protons, you change the element itself. Okay. Electrons, I don't know, but the charge I know is going to be negative 2. So 8 plus something gives me negative 2. 8 plus negative 10 gives me negative 2. This is known as an anion. It is negatively charged. Okay. So what do these charges mean? If it's positive, it means it has less electrons. If it's negative, it means it has more electrons. Simple as that. Let's see. Oh, I'm going to quickly go back to this one right here. Okay. Do you see how this shell, sorry, so something I forgot to mention I just saw. So going back over here, this shell is full of electrons, right? If a shell is full, it's said to have met its octet. So octet means it has 8, okay, it has 8 electrons in it, okay? 8 electrons. However, this one is an inner shell. This is considered inner shell in this example. So octet means 8 electrons. This shell here with this last electron is out. This is known as a valence shell. And this electron located on that valence shell is known as the valence electron. Okay. So octet means 8 electrons. Fills with 8 electrons. Okay. Valence means outermost energy level. And the valence electrons are the ones responsible for bonding. So okay, valence electrons are the ones responsible for bonding. All right, so a little bit of information there on the atom, the atomic structure. Covered some ions, positively charged, known as cat ions, and negatively charged, like an onion, smells bad, anion. Okay, so ions is the changing of the electrons. Remember, there's 3 particles. You cannot change the protons. So we change the electrons. Which one's left that we can change? The neutrons. So isotopes. Isotopes are basically atoms of the same element with different or varying number of neutrons. Okay, and if it has varying number of neutrons, it's going to also have a varying mass number. All right, so let's go over an example of this. Let's use carbon. Okay, the most common form of carbon that we see on the periodic table is carbon 12. Okay, let's have a couple other carbons. I'm going to put the atomic number. It never changes. It's going to be on the top. And put carbon here with a +2 charge, and let's give it that, and this one. Let's do that. Actually, let's make this a 3, 13. Okay, so let's go over the number of particles in each. Protons equals 6 on all of these. Okay, protons equals 6 on all. Now, let's look at electrons. Electrons is going to equal to 6 because they cancel each other out. It's neutral, there's no charge. Here, electrons, we have a +2 charge, so therefore you're going to have less electrons, you're going to have 4 electrons. So far, the number of electrons changed. This is an ion. In this case, I'm going to write it over here. So this is an ion. This one is in its natural state. So natural state, we don't really say anything like this is natural, but I'm just writing it down for you guys to see. This one is an ion because the electrons changed. And let's look at this one. We have 6 protons, no charge, so therefore the electrons equals 6. So not an ion, right? Actually, I don't want to confuse you guys, so I'll delete that. Okay, now let's look at neutrons. 12 minus 6 equals 6 neutrons. Done. Let's look at the neutrons on carbon 13. We have 13 minus 6, which is equal to 7 neutrons. And here we have 14 minus 6, which is equal to 8 neutrons. So here we have an ion, and this is an isotope of carbon 12, and this one is also an isotope of carbon 12. Because carbon 12 is the most abundant and natural common form of carbon. These two are not the natural form. How do you know? You look at the periodic table, right? And the periodic table gives you the mass number, and from the mass number, you're figuring out which one is most abundant. Right? And this is how you see carbon on the periodic table. Okay, so ion and isotope, and then this one is just an isotope. So you're just changed the number of neutrons. So if I gave you an example and I was like, all right, x to the n, and this is y, x to the n of y plus 2, x n to the y plus 3, and z n y. And I said, okay, circle the isotopes. Which ones are isotopes? Well, in order for them to be isotopes, they have to be of the same element. X, 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 same element. Z, that doesn't belong, okay? They have to have the same, we know they're the same element also because they have the same number of protons. However, this one, let's just make this an atom. Make that atom. All right. The mass number in each changes, right? So, same element, different mass numbers. And the reason the mass number changes is because the neutrons change. Remember, mass is equal to protons plus neutrons. If you change the number of neutrons, you're going to change your mass. All right, that is all I have for this part of chapter 3. And the next video, I'm going to show you guys some calculations. Ciao.